This is a revision video for triple AQA physics students only, and it's about changes in momentum. So we have got two equations we previously used. We have got force equals mass times acceleration from Newton's second law, and we've got acceleration is the change in velocity divided by time, which you can also write as final velocity take away initial velocity divided by time. And if A is this, we can swap A for this collected term here. So we can rewrite the equation as force equals mass times the change in velocity divided by time, which simplifies to F equals m delta velocity divided by time. Or we can have A as that package over there and put it into the equation, and F equals m times b minus u divided by t, and that again, change in velocity, simplifies down to F equals mass times change in velocity divided by the change in time. So that is the equation for a change in momentum. So we can use this as any other equation by getting the key information from the question, inputting it into the equation, simplifying, rearranging, getting the answer. But we can also use this to describe safety features and collisions. So why do we use airbags, seat belts, gymnasium, crash mats, cycle helmets, or cushions for playgrounds? Well, the reason why we do it is all to minimise the force. So let's talk about a person and safety features. The mass of the person is constant, and the things that we can control, the things that we can have an influence on, is the time and therefore the force. So if we increase the time, we're getting whatever the mass and this change in velocity is, we're dividing it by a bigger number. If we're dividing it by a bigger number, we're getting a reduced force. If we increase the time, we reduce the force. And if we reduce the force, we're less likely to get injured. So it's a safety feature. So like things for helmets, crash mats, trampolines that people jump out of buildings onto to be caught. We increase the time, we reduce the force. Let's look at this equation from a different example. In this time, we're going to keep the mass a constant, but we don't know what's going to happen to the change in velocity. This time we're going to keep the force constant as well. So for example, it could be a cricketer hitting a cricket ball, it could be a footballer kicking a football, it could be a boxer punching a punch bag, it could be a golfer hitting a golf ball. So we're going to have whatever that force that's exerted is, that's going to be constant. The mass of the cricket ball, or the mass of the football, the mass of the punch bag, or the mass of the golf ball is constant. And we're going to be interested in what happens to this change in velocity. So if we increase the change in time, so if we remain in contact with a golf ball for a long time, we remain in contact with a football for a long time, like we're following through our cricket shot, or following through our football shot, or if we're following through our golf swing, or following through our punch, we need to know what happens to this change of momentum up here. So if we increase the change in time, if we're increasing this, if we were to rearrange this equation, that force gets times by the change in time. If we're timesing by the change in time, the mass times velocity must increase, because this side of the equation is increased. If that side of the equation is increased, then this must increase also. And if this is increasing, this side of the equation is increasing, but the mass is constant, that must mean the change in velocity must also increase. So if we have a constant force, but we increase the time, the change in velocity increases. So we end up with a more powerful cricket shot, or we end up with a more powerful golf swing, or we end up with a more powerful football shot, or we end up with a more powerful punch. If we increase the time with a constant force, we get a greater change in velocity. So that's why you follow through your golf swing, your football shot, your cricket shot, or your boxing punch.